Hi guys, today we're going to do nuclear magnetic resonance. Okay, we are going to look at the carbon-13 and hydrogen. Now, we won't be doing carbon-13 now. We will be doing only hydrogen first. Okay, let me give the colors first. Okay, right, thickness. Okay. See why we for this part here we mainly want to do the molecules of the organic molecules. Okay, so remember here is all on the kind of molecules here. Like I said, simple molecules. Okay, right, molecules here. It's molecules with carbon. So carbon-13 is carbon, but of course here we do protons. So the hydrogen connected to a carbon. Mainly this kind of substances, okay, or hydrogen connected to oxygen, alcohols, carboxylic acids, or hydrogen connected to nitrogen, which is amines and amides, okay, carboxylic acid. All these are protons, okay. So we're going to look at here, proton H1 nuclear magnetic resonance. Spectroscopy means that we use a spectrum, electromagnetic spectrum we're going to use is the radiomagnetic waves, okay? So we analyze and interpret. So we're going to see what is it and see where is it joined to and what kind is it of simple molecules. So here we're going to look at, first of all, okay, we can move this out, okay. Types of protons. Here is types of protons, okay, present in the chemical shifts. So now let's look at the type of protons here. Now in your data booklet, you can see the types of protons here. Now remember this is called the chemical shift. Let me give you the color first, blue color. Okay, now chemical shift, see now, okay, represented in, let me get the thickness first, represented in called TMS. So TMS is tetramethyl silane, okay. Later we see what it means, okay. This is a substance. So this is measured in parts million or Tesla. Tesla is a guy actually, he did a lot of things for chemistry. Okay, now the values here. Actually, the bigger the value here, let's go down here, the bigger the value, higher the energy. Okay, this is a thing to remember. Okay, now here we talk about protons, okay, let's see a type of protons. Okay, so here, for example, this one here is like carbon to H and H and H and H. Okay, it means this can be anything. Normally it's to a carbon, can it even be to a hydrogen? Okay, so here of course it says 3. Of course in this case here you've got three hydrogens here. That means it's connected to another hydrogen, a carbon here. So these 3 fellas here. Okay, so the CH2, which means the hydrogen here connect to a carbon here to a hydrogen here, and normally these 2 connect to a carbon here. Okay, and this is so forth. A carbon here connect to a hydrogen here to a carbon here to a carbon here to a carbon here. So is this particular hydrogens that I talk about? Now, if like for example here there are 3 hydrogens here, so they have the same environment. I mean the same number of neighbors, the same type of neighbors. They are called chemically equivalent. Chemically equivalent. Okay. Here these 2 are chemically equivalent, means same. Okay, they have the same energy shift kind of thing. Later I explain to you what the thing here. So there are 2 carbons here. So same. These are 2. They will give the same kind of signals. This is only one, so it doesn't matter. So in this case here, now if the hydrogen here, remember talking about this hydrogen. Okay. So in this case here, the C, H, H, and H here, and the C double bond O here. Okay, that means that these 3 hydrogens here are also called chemically equivalent. Same number of same kind of neighbors, okay, to see here, but this is oxygen here. So oxygen is electron withdrawing, so it will affect the chemical shift. Okay, so you can see the thing going up. Okay, so this is all about the hydrogen, right? So here, of course, is the hydrogen. This one here. Okay, CH here, right? To a carbonyl compound here, okay, and then to a water carbon here. So these two hydrogens here can have this kind of values here. Okay? All right, now let's look at the main thing here. All right. Now, it says here, the chemical shift, okay? You can see what chemical shift are. Types of protons, I told you already. Relative numbers, all right? How many hydrogens are there? Like for example here, right? So there are 3 hydrogens, okay? They will also tell you in the spectra there are 3 hydrogens, 2 hydrogens, okay? 1 hydrogen, okay? So the number of hydrogens present. Now here, non-equivalent, the number of, from the relative peaks, right? So like this, can go like that, 1, 2, okay. So this comparative is 3 is to 2 is to 1, okay, now peaks. Okay, splitting we'll do later, okay. It's here, pause picture later. Now here, all right, later, we're going to do this one here. Okay, describe the use of tetramethyl, this is TMS, as a standard. That means this part here, for the hydrogen here, we get a 0. Okay, now this tetramethyl is like this. Okay, now this silane here, there's history here. Okay, silicon here. If I want to draw the whole thing like this, right? Okay. All right, so this is called tetra 4. 1, 2, 3, 4. So tetramethyl silane, right? So we're going to see why is this 0 here. Let's go back to theory. Okay, here's the theory. Right, now remember here we talk about a proton. Okay, a proton. It's a proton. Okay, the proton, it means hydrogen here, H. Hydrogen got 1 proton, it's some proton here. And of course, no neutrons, so you have electrons around here. Okay, so electrons here. All right. Now, they say that, remember there's 1 electron here. Electron, there's a spin, isn't it? Spin up and spin down. Or spin clockwise and spin anti-clockwise. Remember you put like a 1s2, so you put the spin up and spin down, isn't it? Protons also can. Okay? Protons, like say there's a spin. Okay? Positive, if it's spinning clockwise, it's positive half. If spinning anti-clockwise, is minus half. Okay? So they all protons are spin, positive or negative. Okay? Clockwise, anti-clockwise. Okay, carbon 13 we'll do later. So now remember, in the absence of a magnetic field, now here, the no field here means no magnetic field. Okay, no magnetic field. Okay, this is called the external field. It means outside I put a magnet. External magnetic field. Okay, they normally put BO or HO. Either way they can represent. So O means here, I'm going to put the field here outside. Okay, the field I can put a magnet here, I can increase it or decrease it. So the value here, this is 0 to 10 here, I can put 1, 2, 3, 4, 5, and so forth. Now without external field, they all will have same energy level. Okay, all these, whether they're spinning anti-clockwise or clockwise, here is clockwise in, right? They all have the same energy level. Like for example here, you can put it down here like that. Okay, here, okay, here, okay. Right here. The difference in between the anti-clockwise and the clockwise spinning is 0. There's no, here is no field. No external magnetic field. Okay? So everything is no difference. But whenever, let's say here is a 0, here to here is 0, the BHO here is 0, 0. But here as I increase the field, the magnetic field, I increase the power of magnet. These two kind of spin will split in different energy levels, right? If this is the magnetic field is on this north, okay, south, okay, it go here, and they found that the spin that is parallel to the external field will have a lower energy, whether it's the clockwise or anti-clockwise, it will have lower energy. Okay, the one that's against the field will have high energy, and if I increase let's say here is 3, here is 5, okay? As I increase it here, the difference in the energy level here will be increased. Now this is equal to H frequency. It's equal to H frequency 2. The H here is called the Planck constant. Now you can see the Planck constant here as you, okay, here. Now Planck constant. Okay, this is here. Now you won't be using a Planck constant. I think only in physics you use the Planck constant. Okay, now mine is the constant here. Okay, so here, now F is a frequency. Of course, F is equal to C over lambda. Okay, this is a wavelength. This is the speed of light. Okay, speed of light. Okay, light speed in a vacuum. Now this is the frequency. Okay, so the frequency can be controlled by shining an energy source. Okay, energy source. Can be light, whatever. Okay, so to flip, when you spin clockwise to anti-clockwise, because flipping. So from here to here, called flip. Flip the spin, F-L-I-P. Okay, so to flip it, it will absorb the energy. To go down, it will give it energy. Okay, now, so remember the difference in energy level here between the two different spins is controlled by the external magnetic field. Okay, so here. Okay, so remember this. Now, you can see from here. So right, now remember the frequency that can flip from bottom to top is in this region here. Now this is the electromagnetic spectrum. Okay, so the radio waves here. All right, that means remember this the bigger the bigger the wavelength, the smaller the frequency. The bigger the wavelength here, the lower this is the lowest energy. So from here to here is increase in energy. Okay, increase in energy. Okay, so that's why the incredible Hulk or gamma rays, X-rays it's a very powerful energy sources. Okay, they cause damage to the skin and cause cancer, whatever. Okay, so they use very low energy. These are low energy sources. Okay, now so these frequencies are used to flip. Okay, flip this one here. So now here you can see. All right, now here let's say these are all same. Now before this is here. All right, I'm going to draw here. There are 5 here. 1, 2, 3, 4, 5. Okay. So now spin upwards here or spin clockwise, whatever. Okay. I'm going to put it to blue. Okay, same as the one here. Okay, here's 1, 2, 3, 4, 5, 6. Now here at this point here, energy HO or BO is equal to 0. Okay, they all have the same energy level, right? Now when I put a fixed magnetic field onto this atom here, okay, let's say 5. Okay, so you split this into all this here. Now that means this energy is after putting the H, the external field equals to 5. This is an external field. External what? External magnetic field. Okay, magnetic field. Okay, so the state is all here. So now here I didn't put. There's no energy. Now here I put energy. Outside I shine a light or whatever. Okay, H field. Now they found that this energy, the difference here is E. Delta E is equal to H frequency mu or sorry H frequency. Okay, here they use mu is here. Okay. Let's say this mu is a frequency, okay? Let's say equal to 500 now, whatever is it. So if I shine the light with 500 here, it will cause this to flip. See, flip spin. It will go up. It will absorb energy to go up here. So remember, this one becomes 2, 4, 6. It becomes anti-clockwise really. Okay. See now. So it will absorb, and this absorption is being absorbed or denoted by a collector. Okay, by collector in the machine. So you will say what is absorbed, what is the frequency absorbed, and the frequency is equals to this. It's recorded by this one here, which is here. You can see here the Tesla. Okay, this is the unit that it will be absorbing. Where is it? Okay, here. Let's see here. Okay, so all this this is proportional to the frequency. Okay, here higher number means a higher frequency. It means the bigger the spin. The energy level between the two different spins will be bigger. Okay, so now let's go back to here again. I'm going to jump here and there. Okay, so normally, right, like here. Okay, normally the low energy will have more protons like here. Okay, the lower fellow will have more like here. Okay, see, right? Okay, there's 6 here, 5 here. Normally here a bit more than this one here. Okay, in nature. Okay, now let's go to here. Okay, now this is a machine. So now this is the magnet. Okay, so they'll produce a magnetic field here. This is where you put your sample. Okay, your sample here. That means your substance. Let's say, for example, your ethanol, C2H5. Okay, dissolve in. Normally they use CCl4. It's a solvent. You cannot use any solvent that contains hydrogen because the hydrogen here will interfere with this hydrogen here. So you can use like CHCl4 or Cl3. This is a chloroform, cannot AA. Unless you change this to a D, CDCl3. Okay, later we talk about this. Okay, so here the frequency, the radio frequency input. So you put here. So it's constant. Let's say 5. You can change the frequency, and if you change the frequency, this thing will absorb the frequency, and it will be shown. It will be collected from here, right? And it will show peaks here. Okay, this is called the spectrum. This the reading here will give you the Tesla. Okay, all right. So this is a basic thing. So now let's go to here first. I want to explain this one here. All right. Now remember, well, let's go to here. Easier to explain this. Now this is electronegativity chart here. I want you to notice the few electronegativity substance you need to know. Hydrogen, because talk about hydrogen, the proton is carbon. Okay, carbon. Oh dear, carbon. I don't know why. Okay, let's do again. Okay, now carbon. Carbon is 2.5. Is 2.1. That means carbon is more electronegative than hydrogen. Okay. Now silicon, very important. Now silicon is 1.8. Silicon is the worst, less than that. Silicon. Okay. So this 1.8, this 2.1, and this 2.5. Remember this. Okay. Now let's go down and let's see this thing called tetramethylsilane. Okay. Now before that, you must understand that now this is the external field. Okay. Spectrometer field. This is called the external magnetic field. H here sometimes it's called B. Okay, you see it's B as well. Okay. Now, of course, you see in all your hydrogen, let's say this is just a hydrogen. Okay, no carbon. So there's a proton here, right? And in all hydrogen, the proton here, right, is surrounded by electron. One electron is free around here, right? So remember, as I told you, the electron has a spin, and whenever there's a magnetic field, the spin created by the electron is always against our outer field. Okay, no, so it's not here. So now, what is felt by this one here is called the effective field. So the effective field felt by the proton is the outside here minus 1. If without this one, if without the electron here, it will just be the HO. Okay, right? But with the effective field, now let's say the field produced by the outside here is 10. Okay, the magnetic field produced by the electron say is equal to 1. So what is felt by this is, well, 10 minus 1. That means it filled 9. Okay, so it will split, right? Split to here. Okay. Okay, so this will be sorry here, and this up here. Okay, let's put 4 here. Okay, so now this will be the energy E1. Okay, H frequency 1. Now let's say here, all right, I now go to this part here. All right, I go to, okay, now this is a key part here. Now, this is the Tesla, this is the reading, okay? Right? Now, TMS here, of course, there's a reading one, but we take it as 0. Like hydrogen has some electrical pull, no, because it's electronegativity, 2.1, you know, but we take it as 0 for inductive effect, you know, okay? So here, now what happens is, now look carefully, this carbon here, I'm just going to draw one of this only. Silicon, hydrogen here, hydrogen here, hydrogen here, hydrogen here. Okay, so there are 4 of them. Now all this, they are altogether 12, isn't it? 3 plus 3 plus 3, there are 12. There are 12 chemically equivalent hydrogen. Chemically equivalent hydrogen. That means they all have the same type of neighbors. Okay, they all will absorb, they all will split the same amount of energy, they all will absorb the same amount of frequency. Okay, that's clear. Okay, now remember, let's say if this, let's say like earlier, okay, without the carbon, okay, that's hydrogen here. Okay, without the carbon, this is the electrons here. The electrons will be all around here like that. Okay, the external field, okay, say we do HO is equal to 10. Now this, if without the carbon, this is only a hydrogen, okay? Without the carbon, goes up, okay? So now this here, this electron here will create, so the field created by the electron is equal to, let's say 1, and it will be against this one. So the effective field, H effective, okay, right, felt by the proton is equal to 10 minus 1 equals to 9. That's all. So if I put this into the machine, it will give me the split. Okay, okay. Now this will be the, okay, this will be, okay, without the carbon. Okay, this is the E1 equals to HF1. Now if I put now the carbon here, okay, now it's with the carbon here. Okay, carbon to hydrogen here. Okay, so remember this, now this one here. All right, now carbon being more electronegative, now it will pull on, it will pull the electron here. Silicon won't pull because it's less electronegative now. Okay, of course some effect, but basically the carbon will pull. Now, all right, now this with carbon, with the carbon covalently bonded to hydrogen here. Okay, now, so without carbon. So now here, right, remember the external field HO is still 10. Okay, same. So now there's less electrons here, right? Less electrons, right? So now it's less electrons here. So of course here the field created by the electron here will be less than 1, is it? That's all. Maybe it's a 0.9 because it's being pulled away by the carbon. Because why? Carbon is what? More electronegative than your hydrogen here. It's not. So now there's less electron here. So the field that's against the external field is 0.9. So what is the effective field felt by the proton? It will be 10 minus 0.9. Is how much? 9.1. Bigger than 9, is it? So remember now the split here, the split for the TMS here with the carbon here will be bigger than this one here. So it'll be like that. I just want a bit bigger, okay? A bit bigger here. So now this one is with the carbon. So the energy level here is what? E2. Because what? HF2. So F2 will be bigger than F1, is it? That's why you need more energy, is it? That's why it's higher here. So here is 0.0 here. Here is 0.9, you know? Okay? See now? Sorry, here. Sorry. I made a mistake. Erase this one. So now remember, if without if without the carbon, right, it'll be here. Okay? Right now. So with the carbon is here. Of course, here will be a value, but we take it as 0 here. Okay, now so here we represent this F2. Okay, right? with the carbon here. Okay, now to the silicon. Okay, now I've got this one here. See? Okay, now carbon here same. Look, now watch here. This here. Okay, this same as here. This one here. Okay, right? Instead of silicon, I've got carbon here. Okay, so now this electron here. Okay, right? At first, without the carbon is 1, no, the field created by electron. But now with this carbon here, it's gone down, right, to 0.9. Now got one more carbon here, pull some more, right? Pull and pull. So like here, right? So the 2 carbons here. Here's carbon, silicon, here's carbon here. So pull more. That means the electron will pull more, right? Now that means here the field that's going against the outer field, which is your HO equals to 10 here, is going to be electrical field. How much? If here is 0.9, it means here is 0.8, less than, right? So the effective field felt by this proton here, okay, I'm going to put a red color now. Okay, that means the effective field. Okay, I put, well, 2, okay, field by now is equals to what? 10 minus 0.8, which is how much? 9.2, bigger than here, isn't it? That means now the split is bigger still than here, bigger. So this E3 equals to H mu 3, and this is the one here. See now, higher frequency means higher energy, is it? See now, so it's going downfield. It's called downfield. Or higher energy, okay? See now, okay? So because electrons are pulled away from here, the electrons density here is lessened, right now. So it have a less field against the outer field. So the proton here will feel more of the magnetic field. So it's split bigger. Now let's see like here. Oh yo, this one is it. Okay, now carbon, hydrogen here. Now of course the 2 chlorine, they are even more electronegative. I'm going to put blue color. All right. See, they will pull and pull. Now the electron field, the electron density here and here, these 2 are same. They're called chemical equivalent. Right now. So they are being pulled. So the electron pull out here, pull out here, pull out here, pull here. So that means the electron around here, around the hydrogen, is less than much more. Okay. So less that it will give you a electron, the field created by the hydrogen electrons here going down here would be much less than, because all electrons are being pulled here. So maybe it's even 0.7 only, or 6. They put 6 better. Okay, put a better value. Erase 6 here, right? Okay, so it goes to 0.6. Okay, so what is the effective field felt by these 2? The H effective is equal to 10 minus 0.6 is equal to 9.4. No, bigger not. So the difference between here and here will be bigger still. It's not. Right? E is equal to H frequency. That means this 4 here will be much bigger. Sorry, it's going down here, 5.3. So it's saying as the carbon that's joined to the hydrogen here is connected to things, atoms which are more electronegative, the electron density here is the hydrogen is lessened, right? So it will be less electric field by the electron here, so it moves downwards. So give a bigger value here. See now, okay? You can see down here. So like here, right? Here the carbon, hydrogen here, connect to oxygen. Oxygen is very electronegativity. So pull. So here will be less electrons. So less to go against the outer field. So you feel more of the field. So you have a bigger value here. Understand? Okay. Now you can go over and think over again and play the whole thing again. Okay, and you see what I mean. Now, so the whole thing is electronegativity. Now here I will talk about now on the here on the benzene ring. Okay, the benzene ring is a bit different. Now this is the benzene ring, the carbon here. to a carbon here, to a carbon here, to a carbon here, to a carbon here, okay, to a carbon here, and so on. Now this is a hydrogen, okay, hydrogen. Now this pi electron cloud here, okay, on top here and bottom here, okay, they will create by themselves a magnetic field, which goes in and come out here. See now? Okay. Now as it comes out here, this field B for benzene here created here is a small amount. Let's say it's 0.5 here. Right now this external field BO goes to 0, 10. So now together this plus this will be, see now, so there's like a extra magnetic field on this hydrogen. See now? So it's now B effective field is equals to what? BO plus the BB, which is 10 plus 0.5. You know? So if field small field, that means I will split more, not big. Okay? So the hydrogen in a benzene ring, right, has pretty high value. See now? See here? Okay? 6 to 9. Okay? Because of the field, the magnetic field created by the pi electron cloud is going alongside with the external field. It always goes alongside. Okay? Now that's for benzene. Now for alkenes, about the same idea. Okay? Now here we talk about alkenes here. Okay? Alkenes. Now this is alkene. Okay? Now this hydrogen here. Okay? Now this pi electron cloud, okay, go down here. It will create a field going down and up. Up. So the field created by the pi cloud is going up here. So it's a field by the pi electron cloud here. So same direction as the external field. So the hydrogen here will feel, so the effective field is equals to the external field, right now, plus the field created by the pi electron cloud. That means addition. That means split more, isn't it? Just split more. So I said, so it's a high value here. Okay, 1 point. So the hydrogen here will have a absorption of 1.8 to 3.1, pretty high. Okay. Now, but sorry here. Sorry, I missed it. It's not. Okay, it's the one here. Just now I tape didn't come out. No, so I can do it again now here. Okay. So now for the triple bond, it's a bit different. All right, triple bond, you have to align it like this. Okay, and of course the pi electron cloud here create a field. So say it goes up and here it will go down. You know? So it go down onto this fella here because this position is here. So now remember this external field. So what is felt by this one is of course the B effective equals to what? Equals to B or minus because going down against it. A B E. Okay, so it's a bit lesser. So it's lower than your alkenes here. Lower than alkene. Okay? See now. So that's how I explain it. Now you can see here for like okay, now hydrogen to carbon here. Now this is a very strong electronegative. Okay, this is aldehydes. Okay, right? Aldehyde hydrogen. Okay, RZ. So pull here, it will cause it to be split high value. Okay, now for alcohols also, because this is to oxygen, not to carbon. Oxygen is very high electronegativity, so it's 0.5 to 6. Also, in this case here, there are not enough oxygen, but also there's a carbonyl group here. So for carboxylic acid, very high, 9 to 13. For amines, also same. Amines and amides nitrogen. Okay, so nitrogen pool is a high FON, high electronegativity FON. Okay, so pull it, so 1 to 5. And for amides, it's 5 to 12 because not only hydrogen, nitrogen, but also oxygen here pulling. Okay, so here the electron density around here is very much lessened. Okay, so less that the magnetic field created by electrons around the hydrogen here is less. So you feel the outside more. Okay, so it's like split more. Okay, now this is a basic thing about NMR. Okay, you go back and listen again and then look at these examples. Okay, now you can see here examples. I'm going to go straight here. So remember the spectrum, the NMR spectrum gives you a few information. The first thing, of course, is a number of signals, the kinds of protons, the type of protons. Okay, right? For example, here. All right, let's look at this first. Okay, now this one here. This is your 1-chloro, okay, or chloroethane. chloroethane. Okay, no need one now because over here. Now remember this hydrogen here and this hydrogen here. Okay, right, this hydrogen here, there are three of them here. Okay, so these three hydrogens here are chemically equivalent because they got the same type of neighbors. These two are chemically equivalent. But this, of course, is to a carbon and then to Cl. The Cl will pull, but it's more effective on here, isn't it? So this is less effective. So this one will give you a signal. Because the same, there's one signal here. Okay? Right? Now remember this CH3, so what signal is it? Well, it's around here. This one here. Alkane. Okay? Right now. Right? To C, so, right? 0.9 to 1.7. So probably because if it's 9 here, that means it's a C here, right? Okay, right? And of course, there's a H here. But if a Cl here, that means it pull more, it will split more, isn't it? So maybe 1.2. So I put here is 1.2. So this will be giving a 1. If you put like that here, your TMS is 0. It's 1, 2, 1, 2. So it's 1.2 here. So you go like me, okay, and you go up here. Okay, go down. Now this one here is this hydrogen here. These two are same the chemical equivalent. Now it's joined to a chloro. No, it pull here. That means the electron density is less enough. Okay, so you will see that. Well, what signal will give me? Like here. Okay, here. Next to electronegativity here. See? So this Cl will pull with the electrons here. So it's 3.2 to 4. Okay, so about maybe 3.2. So here, this is 3. So this will give me 3.2. So this is 3 here. See? So you go up here. Now you'll get a lower value. So remember the area under here, right? Or the height here. Here's 3. Here's 2. So the area under the stick here will tell you the number of protons of this type of proton. The type of protons. Right, the type of protons here is CH3 protons next to a C. This is the CH2 protons next to a Cl. So and the number of protons. Okay, so there's the area here. Now here, of course, these two here. These two here. The hydrogen here will be are same because why? We have the same kind of neighbors. Yeah, okay, so these two, 6 of them. Okay, so of course these 6 will have around the same one like here, right? This one here. Okay, this one here, CH3 isn't it, right? But this value here, okay, around 0.9 to 1.7. So here, if you draw a diagram like that here, okay, 0, 1, 2, and 3. So this is about 1. Let's say this 1.2, 1.2. Okay, so here 1.2. So there are 6 of them. So go like that and go up here. Okay. Now because this H here, and it goes into carbon and to a Cl here. Okay, Cl here. Okay. So the Cl will pull the electrons. Okay, pull here. So of course, is this one here? See now, this one here. See? Okay. Carbon H naught. So maybe about 4. Okay, 4. So here. So it's about 4 here. There's 4 here. So then only one hydrogen. So you go down here, and a small peak here. So it's 1 is to 6 here. So the area of the peak will tell you the number. So there are 2 peaks, tell you 2 types of hydrogen. Now here, okay, for this one here, this 1 chloropentane. Okay, so of course this 3 hydrogen here we are chemical equivalent. So you one type of peak. Here's one type of peak. So 2 different ones is nearer to chlorine. This is the nearest here. So of course you form 3 peaks here. Okay, TMS here. Okay, 1, 2, 3, and 4. So this is about 0.9 to 1 again. So that's about here, about 1. Okay, so go up here 3. Okay, this next to here about maybe let's say CH2 to C. So remember, it's still around here. Okay, right? Okay, a bit further down because it's near to the chlorine, is it? So maybe if here is 1.2. Okay, here will be if this 1.2, this is 1.4. Okay, so 1.4, another one here. So 2. Okay, and this next to chlorine, right? Next to chlorine is what? Next to chlorine will be, check it out. Chlorine, okay, over here. So I said, okay, 3.2, 3.3, let's say 3.3. Very near chlorine here. So it's 3.3. Okay, this will be 3.3. So go up here, and then with the same height as this one. So it's 3.3. Okay? So it's 2 is to 2 is to 3. See? So this is called spectra. It tells the type of a proton and the number of protons. Okay? All right, now let's go some more. Give more examples. More examples. Okay. Now here you can read out well, how the electronegativities affect the shift. Okay. Now let's look at this. Now this is your metapropanoate. Let's draw the whole thing out. Okay. Okay. All right. Okay. Now, how many types of hydrogen are there? Let's put red down. Okay. Now, these three, of course, are chemical equivalent. Okay, because same type of neighbors, ma. These three also chemical equivalent. So this, okay. So this is nearer to the oxygen. This is further away. Now, these two are called chemical equivalent, are nearer to the carbon dioxide. So there are three types here. Three types here. So which is which? Of course, remember this hydrogen to a carbon, then carbon to oxygen. So of course this one will be about 0.9 to 1.7. Okay, right? I put red here, so it's a bit different. Red. Okay, this one. Okay, so that's why. Okay, stay. Oh, here. 1 point. What 1 point here is maybe 1.2 lah. Okay, so this represents one here. The three of them. Okay. Now, here of course it's lower, 2 point something, right? 2 here. Now see here, this carbon next to a carbonyl group. Okay, now check it out. You can check out from here, carbonyl. Okay, see now. Here then, okay. So 2.2 to 3, okay, see now, 2.2 3, right? So next to carbonyl. Okay, because there's a carbon separating oxygen from carbon here. So of course this will be 2 point something. So this one here. So this is the one here. So this is okay. So 2.4. Yeah. Okay. Now this one, this hydrogen is next to carbon and to oxygen. It means stronger pull. This one is separated by one carbon here. This one with no carbon and oxygen. So stronger pull. So CH3 to O. Can see here? Here CH3 to O. Right. 3.2 to 4. Right. Which means 3.2 to 4. To 4 here is here's 3.7. Okay. So this is you see the height. 3 is to 2 is to 3 now. Yeah. 3 is to 2 is to 3. Good? Okay? So you can see the types of hydrogen and the number of hydrogen. Now this of course is called a spectrum. Now this is low resolution. Later we look at the high resolution which is splitting up. Okay? Now, this is called the spectrum. Or spectrum. Okay? Now some more examples here. You can read up here. Okay, explain on here. Okay, now here we have got example 1. Now this is a spectra here. Okay, this is the spectra. Parts per million. Now this is a Tesla. Of course, 0 here is for TMS. Okay, so what are these? Got 3. Of course, 3 is 2 is 1. It means this is only one hydrogen here. 2 hydrogens and 3 hydrogens here. And of course, now there are 3 types of substances here. So which one shows this spectra? Okay, now let's look at it again. Slower down here. Let's look at propanoate and see how many types of hydrogen are there. There are 3 types, 1, 2, and 3. So there are 3 signals. It's not. Is that here? 2 signals not. Yeah. Of course, that means it cannot be this one. Okay. So 3 signals. 1, 2, 3. It's not. Now it's very easy in this case here because this fellow here is very high now. Okay, about 11.6. Okay. Right, 11.6 normally is shown by your carboxylic acid here, right? Hydrogen to oxygen, okay? Right? Okay, now remember these 2 are same, about the same. Okay, these 2 are about the same. CH3 to C is it? C to C. So is these 2 here will have this one. Okay, right? 0.9 to 1.7, okay, which is, see that, 1 point something, right? This is your CH3 to a C, okay, which is this one here and this one here, okay? Now, next one, this one here, CH2 to O and CH2 to CO. Of course, this will be lower than this now, right? CH3 to O are nearer to oxygen, so it's be higher. Let's say CH2 to O, CH2 to O. Now, CH2 to O should be 3.2 to 4, isn't it? Here's what? Here's 2 less than 3. See? This is less than 3. This is CH2. Okay. Off it first. Okay, never mind. Okay, remember this is CH2 to C and to O, okay? May separated by a C here. So what is this? C here. Okay, see now. CH2 to here. Okay, it's not here. Okay, so about less than 3, 2 point something, which is correct. 2 point something, maybe 2.4. So this is this to explain this one here. Okay, right? So of course, propanoic acid is the one. Of course, this is very clear. See, why not? Here is like an aldehyde. Okay, here is carboxylic acid. See, carboxylic acid is way up here. See, see, way up here, carboxylic acid. See, right? Unlike your aldehyde is here. Okay, so it's very high, near 13. This one cannot overshot 10, cannot overshot 11, and here is about 12, I think, right? 11 point, see, 11.6 here. So, okay now. So you go over and see how all these things relate. Now here it explains to you. Okay, now here, right? Low resolution. How we distinguish between propanon and propanol? Very simple. This fella and this fella here are chemical equivalent, same type of neighbors. So give you only one peak. This is called a peak. Okay, only one signal. Here got 3 peaks. Chemical equivalent 1, 2, and 3. So 3 peaks here. Okay, all right. Okay. Now, well, for next one we will go to splitting. All right. So I finish here. I know I rushed because I did the first one but didn't came out, so I wasted my time, you know. Okay, we going to stop